Okay, so to quickly review what we did until last week, we just go through the content. The first week of class, we said it's important to consider the effect of a connecting wire between your source and the load, especially when you have high frequencies or when you have long distances. Thank you for coming in the front. And he said this is all because of the electromagnetic field picture acting, but instead of getting down to electric field and magnetic field, let's try and analyze this in terms of the voltages and currents that we know about from our circuit theory. And what a transmission line does is it delays. And we know very well from our circuit theory that we can model the delay using capacitors and inductors, and the capacitors and inductors need not be perfect, so we included the resistance and conductance, resistance of the inductor and the conductance of the capacitor. We wrote down, we had a simple model for the transmission line, and then we wrote down the Kirchhoff's voltage law and current law, got the propagation equations for the current and voltage. It was a coupled differential equation. Some stage we said let's work with sinusoid, a single frequency, so that things become easier, and we use the complex notation, worked out the differential equation for the propagation of voltage. This equation does not have time because you know how is it going to vary as a function of time, because it's a simple sinusoid. And we had this definition here, which is something which you need to remember, the gamma, the propagation constant. And we realized that the solution is the sum of two waves. That's what we reached the other day, the last class. So here is where we are right now. If I have a transmission line at any point Z on the line, what I know now is that the voltage, if I try to measure the voltage, I see that this is the sum of a forward propagating wave and a reverse propagating wave. So at any point, see, we did not put any boundary condition, we just took the line. We did not say that what is the source, we did not say what is the load. All what we are saying is that the line can support two waves, one propagating in the forward direction, the other propagating in the reverse direction. There was a question which came to me as an email after the last class. I said that I will answer this the first thing today. The question is, when we analyze this forward propagating wave and the backward propagating wave, we said we did that analysis by taking at a given time and at a given Z. The question was, why did you take Z equal to 0 and T equal to 0 for this analysis? Or is it true only for Z equal to 0 and T equal to 0? Why would I do that? The answer is very simple. You see, this is a cosine function. So at a given T, if I want to analyze, I could very well take a T which is not equal to 0. So that would mean that cos omega some T, let me take T as 1 second, then I would have omega 1 minus beta Z plus phi plus. My answer is not going to change. The behavior of the wave is not going to change as a function of Z, because All what this time is doing is just adding a constant phase. That's all what it is doing. So omega times 1 minus beta z plus 5 plus if I analyze, in fact I even put 5 plus is 0, this is 0. The reason I did is so that it's easier for me to write down what is or to draw this wave. I could very well have this omega and phi. The answer would be different because at z equal to 0 I would not have cos of 0, I would have cos of some number, some angle, and corresponding to that some angle I could have a certain cosine value for cosine. But this omega into 1 plus 5 plus being a constant, the behavior of the function as a function of z is not going to change. It's still going to oscillate around z, except that I've added some phase into it. So my interpretation of the result is not changing at whatever time I consider. Similarly here, my interpretation of my result is not changing. Here I am looking at cos omega t minus beta z as a function of time. I could put z equal to 0, I could put z as any 1 meter, 2 meter, whatever length you wish. All what it does is it just shifts the cosine wave, it just shifts the phase of the wave. The nature of the wave does not change. So I hope that answers that question. So the next job is to figure out what are these waves. We just wrote that the sum of forward propagating wave and the backward propagating wave. The forward propagating wave has this as the amplitude. As a function of z it is decaying because there is an e power minus alpha z, and it is characterized by this cosine function, and this is the backward propagating wave. So if I were to find out what is this wave, if I were to measure what this wave, I have to put an oscilloscope probe and measure this voltage. Question I am asking is, what is the voltage that I would measure? How much voltage would I measure? Would I measure 5 volts, 6 volt? Would that voltage change as I move the probe along the z? That's a question I am asking myself. So essentially what I am trying to do is now to figure out the unknowns in the system. Now what are the unknowns here? Omega is a frequency that is being applied. So let's write down what are the unknowns in that equation. Omega is the frequency that I am applying, that I know how much frequency am I applying. I had, let's just write down the constants there. I know I had a V plus, mod V plus, I have a mod V minus, alpha, I have a beta, and I have an omega. And I have a phi plus and a phi minus. This phi plus is the phase associated with V plus, and phi minus is the phase associated with V minus. Okay. So to say V naught plus is what I wrote as V naught mod V naught plus e power j phi plus. So essentially what are the unknowns here? Remember what was alpha and beta? We wrote gamma, which is under root r plus j omega L times g plus j omega c. This we represented as alpha plus j beta. So if I have picked a line, if I have decided that my transmission line is a coaxial cable of a certain length, I have already defined my wire, I have already defined my line. For example, if this is my transmission line, I know that what is the conductor here, what is the resistance of the conductor, how much is the capacitance between the two live wire and the ground wire. I know all the details of this wire. So which means that I can actually measure R, I can measure inductance, I can measure conductance, I can measure capacitance. All what it needs is a multimeter which can measure all this, right. If I take a coaxial cable, this is my coaxial cable, the center line is hot line, and then you have the ground. I look at the cross section, it is like this. You have a dielectric here, alright. I can measure what is the resistance of this, inductance, conductance, capacitance, all that numbers are measurable quantities, which means I know what is alpha and beta once I have picked my line. Omega, as I said earlier, is a frequency that you are applying, so that is also known to you. So if R, L, G, C is known, alpha and beta are known, omega is known. What is unknown here? The only unknowns you have are these voltages, the amplitudes of the forward propagating wave and the backward propagating wave. Those are the unknown voltages, unknown quantities in this problem. The question is, how do we find those quantities? Intuition says that the voltage that will get developed across this line obviously should depend on what you apply here. It should depend on what you connect here. So now we bring in this boundary condition. Because your unknowns are V0 plus, the complex V0 plus and the complex V0 minus. Now to find this unknowns, we are going to use the boundary conditions. What we are also going to do is to simplify the solution. We are going to assume an ideal transmission line. Now, what is an ideal transmission line? At this moment, we would say that ideal transmission line is the one that would just delay the signal, that would not attenuate the signal. Okay? So, when I say ideal, now what I mean is lossless line. There is also ideal transmission line would also mean a dispersion free line, but we will consider this aspect of dispersion a bit later. Let us just stick to lossless line now. Now, what is the meaning of lossless line? It simply means that, of course, there should not be any voltage loss in the line, which would mean that the L should be ideal, there should not be any resistive drop in the L, and there should not be any resistive drop, or there should not be any ohmic loss in the capacitance. How would you avoid resistive drop in the L? You would say, demand that the resistance is 0, and in the capacitor you would demand that the dielectric between the plates of the capacitor is having infinite resistance. So, which means G is equal to 0. That is the meaning of lossless line. You will see naturally that when you put R equal to 0 and G equal to 0, your gamma with R equal to 0 and G equal to 0 would mean J square omega square LC, and so this would be J omega under root LC. And comparing this with, we defined gamma as alpha plus J beta, this is now J omega root LC, which means alpha is 0, beta is omega root LC. So, for a lossless line, it turns out that alpha equal to 0. Quite intuitive, because if you go back and look at the way the wave is propagating, you see the forward propagating wave V0 plus e power minus alpha z, right. So, here you had alpha sitting here. What was this alpha doing? E power alpha z would mean that if I had non-zero alpha, it would mean that the voltage as a function of position is actually decaying, because there is an attenuating e power minus alpha z factor along the length of the line. Now, if I consider lossless line, all what I am saying is that this alpha is 0, so the voltage does not decay, it remains constant as a function of z. That is what it means physically. So, if I consider a lossless line, I know my alpha is 0 and your beta is root LC. This would also mean that the velocity, we discussed what is the velocity with which the wave is propagating. Yesterday we said that this velocity is omega by beta. So, this velocity is Vp is what I am calling as velocity, omega by beta, which is 1 over root LC is a constant. It is not depending on the frequency. All the frequencies are propagating with the same velocity, which simply means that whether I connect 1 gigahertz or 100 megahertz or 1 kilohertz into the line, all these frequencies are propagating with the same velocity, right. We will discuss later that when there is dispersion in the line, it would mean that different frequencies would start propagating with different velocities when there is dispersion. When there is dispersion, you would realize that this omega p becomes a function of frequency. Anyway, for this case that we are considering, there is no dispersion. Now we go back to the boundary condition. Remember, our objective is to find out what is V plus and what is V naught minus. So, we are going to consider the line. Let us say Vg is my source. Let us say my internal impedance is Zg, is connected to the load ZL. ZL could be complex, it could have resistance, capacitance, inductance, and this is the line. Now, you have fixed the boundary conditions now. What are your boundary conditions? At the end of the line, I have an impedance ZL. At the beginning of this line, I have a voltage, I applied a voltage Vg. Now, let us say L is the length of the line, and let us say Z0 is the characteristic impedance of the line. Why are we calling this as characteristic impedance? Because Z0 is actually telling you the quality of the line, what is the resistance, inductance, etc. Now, what we are going to do is, we are going to define the coordinates. See, all this while we never said what is the position of Z. I mean, where is your Z axis located? The Z axis obviously is located along the line, but I have the freedom to choose Z equal to 0 here. So, I am choosing Z equal to 0 here. Z is equal to, since I am going in the negative direction, this is Z is equal to minus L. L is the total length of the line. So, I know that Vz at any point in the line is a sum of the forward propagating wave V plus e power minus gamma Z, but gamma in gamma my alpha is 0, so this is simply minus j beta Z plus V naught minus e power j beta Z. And we also can write Iz as V naught plus by Z naught, because yesterday we derived that V naught, the ratio of V naught plus to I naught plus is Z naught, e power minus j beta Z, and a minus V naught minus over Z naught e power j beta z. Already. I am going to apply boundary condition. What is the boundary condition that I am going to apply? I am going to say that at z equal to 0, the impedance is ZL. It has to be ZL because I have physically put an impedance ZL there. So if I can measure the voltage across this as VL, the current through the impedance as IL, what I am demanding is VL over IL should be ZL. That is a boundary condition. But my analysis of the line says that the VZ should be this. So where is the location of my load? I have conveniently chosen the location as Z equal to 0. So at Z equal to 0, this should be whatever I measure across the impedance, the load impedance should be equal to VL. And I put that condition on this equation, I get V0 plus V0 minus, because at Z equal to 0, e power j beta z and e power minus j beta z reduced to 1. Similarly, I at Z equal to 0 is the current through the impedance, and that should be, I just substitute here in this equation and I get V0 plus by Z0 minus over Z0. And the boundary condition is the ratio should be ZL, which means the ratio of these two should be ZL. Take the ratio, I get V0 plus V0 minus divided by V0 plus minus V0 minus times Z0 is ZL, which means ZL by Z0 is, well, I am just algebraically manipulating this, and I get this. The ratio of the load impedance to the characteristic impedance turns out to be something that has to do with V0 plus and V0 minus. Physically, what is V0 plus and V0 minus? V0 plus is the amplitude of the forward propagating wave, V0 minus. So if I can imagine that I have a, is there a problem? Yeah. The size changed a bit, but does not matter. So, well, we can think about V0 plus as, I can think about it as a sum of forward propagating wave and a reverse propagating wave. The forward propagating wave has an amplitude corresponding to V0 plus, and the reverse propagating wave has an amplitude corresponding to V0 minus, and the ratio of the two amplitude sets is what is given by this. Now let me define ratio of the amplitude of the reverse wave to the forward wave as gamma, so V0 minus by V0 plus. Okay. Now you define this ratio as the voltage reflection coefficient. Now, where is this reflection coefficient coming from? Where is reflection coming from? The whole problem now you can look upon like this. You can imagine that you have excited the line with a frequency, it is setting up a wave propagating in the forward direction. You have a load at the other end. It's as if there is a reflection happening at the load, otherwise why should there be a reverse? Why should the transmission line support a reverse propagation? So it is as if the source has excited the system with the wave, forward propagating wave, and the load has reflected a part of that voltage back to the source. And in that sense, you call this ratio as voltage reflection coefficient. So I can actually do an algebraic manipulation on this. I can divide it by V0 minus, add and subtract 1. I can actually, from this equation, I can write ZL minus ZO as, if I divide it throughout by V0 minus, V0 plus, I get 1 plus gamma over 1 minus gamma. So I get gamma as ZL minus ZO over ZL plus ZO. Algebraic manipulation. What is the physical significance of this equation? The physical meaning is the following. If I have a line with characteristic impedance Z0, I am connecting a load of impedance ZL into the line, and if Z0 and ZL are not identical, if Z0 and ZL are not identical, this implies that gamma is non-zero. Gamma is non-zero implies there is a reflection. The system is supporting the backward propagation. So let's take the case where ZL equal to Z0. What happens in that case? If I have ZL equal to Z0, it means I have matched my load impedance with the characteristic impedance of Z0. If that is the case, my gamma is 0. Gamma is 0 means no reflection, which means it actually means V0 minus is 0, alright. I have only forward propagating wave. It's as if the voltage that the source, whatever is that voltage that source is setting in, it's propagating in the forward direction and that is getting dropped at the load. Nothing unusual happening. But that happens only when ZL equal to Z0, whenever you are matching the load impedance to that of the characteristic impedance of the line. Suppose that is not the case, ZL is not Z0, what happens is gamma is not 0, which means in this case you have a reflection voltage reflected, which is gamma times V0 plus. It's as if a gamma fraction of the incident forward propagating wave is getting reflected back into the system, which is something that you do not want. you want to convey the energy, you want to transfer the energy from the source to the load. You don't want it to be transferring back to the source. Could be dangerous at times. If the source is not sufficiently protected, you will have the voltage coming and hitting back at the source. And that is always going to happen if you are not taking care of ZL equal to Z0. Remember, in your circuit theory, you learnt that maximum power transfer, you have learnt about the maximum power transfer theorem. What does that say? It says maximum power is transferred from the source to the load when the load impedance matches with the internal impedance of the source. You are able to transfer maximum power. So this is circuit theory, which says that, you know, if I have a Vs and a Zs internal impedance, ZL is the load impedance, you will transfer maximum power when your ZL is matching with Zs. You did not bother about the line here, what connected the source and the load. But when the line becomes important, which is the case when you have large frequency, long lengths, whenever transmission line becomes important, impedance matching means something else. Impedance matching means you are creating a situation where you do not have reflected voltage, and that can happen only when the source impedance, when the load impedance becomes equal to not the source impedance but the characteristic impedance of the line. So finding that characteristic impedance of the line is very important. How do you find the Z0? You essentially calculate RLGC. It's very important because only then you don't have reflection. Now let's take the case when you are having an open circuit situation. Open circuit would mean ZL is infinity. Gamma is ZL minus ZO by ZL plus ZO. So I could write this as 1 minus Z0 ZO, whatever you call that as. And substitute infinity, I get 1. What does it mean physically? This means that I have a transmission line which is open circuited. I excite with a voltage. I have a forward propagating voltage in the steady state. The entire voltage is getting reflected back in the system. Which means that high frequency circuits never leave it open. Always turn on the high frequency circuit with some load or ideally a matched load. If you do not load the circuit, let's say you made a high frequency voltage oscillator for your project, some 3 gigahertz oscillator, you struggled and you make your 3 gigahertz oscillator. But if you do not take care to load that before you turn it on, what's going to happen is this voltage is going to go back into your oscillator. And if the oscillator does not have enough isolation, the IC does not have enough protection, this is going to go and damage the oscillator itself is going to act as a load because the entire voltage is going to go back into the IC. That can simply damage your circuit. So take care that when you are open circuiting when you are doing an open circuit on a transmission line, the entire voltage is going to come back into your source. You thought about it as a case only when you have short circuit in electric circuit. In a basic circuit theory, you were always wary about short circuiting. Now here we are saying that even open circuit is as dangerous as a short circuit. What happens in short circuit here? Your ZL is 0, connecting the two ends of the wire. So what is gamma? ZL minus ZO by ZL plus ZO, the minus 1. As damaging as open circuit, except that there is a phase change of 180 degree. Minus 1 is indicating that the reflected voltage is not in phase with the incident voltage. When V0 plus is positive, V0 minus is negative. That's all what it means. But the entire, in terms of magnitude, the entire voltage is reflected. So as far as the transmission line problem is concerned, what we did was we applied this boundary condition. We found out what is the reflection coefficient. In a way, we were writing V0 minus as gamma V0 plus, and the gamma is decided by ZL and ZO. So the beginning of the class we said there are how many unknowns? We have two unknowns, V0 plus and V0 minus. By applying a boundary condition, what we ended up at the end of the class today is, I know V0 minus so long as I know what is the load that I am connecting and what is the transmission line I am using. So the only unknown now is V0 plus. Because I have figured out a way to calculate, if I know V0 plus, I can calculate what is V0 minus, purely decided by ZL and ZL. Of course, we said the implication of having short circuit, open circuit. In fact, in general, your ZL is complex. My load could have a reactive part, a resistive part, which means in general gamma. What does it physically mean? It physically means the following. Think about it as, let's say, load end Z equal to 0. I am trying to see how my V0 plus, only V0 plus is propagating. Gamma is complex would mean that I have amplitude e power j theta gamma, the phase for gamma V0 plus. Simply means that V0 minus is not in phase with V0 plus. There could be an additional phase gamma. Physically, what does it mean? It means that the reverse propagating wave need not have its amplitude positive when the forward propagating wave is at its crest. The reverse propagating wave, of course, has its magnitude, the amplitude not equal to V0 plus in general. Of course, in open circuit and short circuit case, it will be identical to that of V0 plus, but in general there is a gamma factor. So the amplitude of the reverse propagating wave need not be the same. So this height, let me draw the reverse propagating wave. This is in general the reverse propagating. The heights need not be identical and the peaks need not occur at the same Z. That's the meaning of having gamma complex. There is an additional phase difference between V0 minus and V0 plus. So if we try to track the crest, they need not be lined up. That's what it means. It also means one more thing. So if I have a transmission line and I try to probe with an oscilloscope what is the voltage, resultant voltage, I cannot isolate the forward propagating wave and the reverse propagating wave. What I see is the resultant wave. So at a given Z, what I see is the sum of, at a given z, what I measure is the sum of plus propagating wave and the minus propagating wave. And you know from your basic mechanics that if I have a forward propagating wave and a backward propagating wave, which means I have an excitation moving in the forward direction, I have an excitation moving in the backward direction, what I end up is with a standing wave. And what I would actually see is the standing wave. That's okay. But they are not seeing the right side, it's, a part is getting cut. Yeah. Anyway, we'll deal with it tomorrow, it's almost over today. So I'll write on the left side today. Yeah. So what we are seeing, if I put an oscilloscope and try to measure, what I would see is not this independent V naught plus and an independent V naught minus. What I would see is the sum of these two at any given z. So at any given z, I would see this plus this. At this z, if I am measuring, I will see this plus this as my result. So we will talk more about the standing waves and how would they look like in the next class. I will try and show you a simulation on how the standing wave is evolving. Remember, there is a function of time also which we are skipping here. This is all a function of space. So as a function of time, there is a periodicity. So I will try to show you a simulation on how these standing waves are behaving on the transmission line when you have different load conditions. That we will do tomorrow. To sum up, what we did today is to start from this point where we realize that the only unknowns in a transmission line is now V naught plus and V naught minus. Applied boundary condition just by putting a load at the end of the line. Figured out what is ZL. All what we demanded was at the load you would have the impedance VL over IL as equal to ZL, and from there we defined the reflection coefficient, and we look upon the problem as the following. If I have a transmission line connected to a load, you can justify the reverse propagating wave if you say that, okay, a part of your incident wave is getting actually reflected back unless it is impedance matched. We looked at the condition for impedance matching. Impedance matching would actually mean ZL equal to ZO. This is the golden rule now for impedance matching, that I should have ZL equal to ZO. That is a condition for your impedance matching in transmission line. And we notice that this is different from what we learned from circuit theory for maximum power transfer theorem. Look at the comparison there. And we also realize that the problem now is reduced to finding this unknown V naught plus. And I said that we will talk about standing waves, which is actually the resultant of the forward and the backward propagating wave. That concept we will come to in the next class. So I close the session now and open it, the teaching part now, and open it to questions. So if you have any questions, please hand raise. So connected to VCAP. So VCAP, do you have any questions? I mean, I'm connected to many, but I can see VCAP plus.
Good morning, madam.
Good morning.
What will happen if load impedance is greater than characteristic impedance?
What will happen if the load impedance is greater than characteristic impedance? What will happen? I will have this. So I will have, depending on what is ZL, whether it is real or complex, I will have some gamma. Whether ZL is less than ZO or ZL is greater than ZO, I would have gamma which is non-zero. I would have reflection setting up in the system. I have reflection set up in the system. So the point is this, in a simple circuit theory you thought that to connect the source to the load and everything is done. Energy is transferred from source to load, take care of impedance match, energy is transferred completely from the source, or maximum power transfer it can happen. But the moment you start looking at the transmission line concepts where which is again when the frequency is large and when the length is large, what you would see is it's not simple. Energy is going from the source to the load and it's getting reflected back to the source. So that's the point here. Whether it is ZL is greater than Z0 or less than Z0, so long as it's not equal to Z0, you are having this energy going back and forth. All right.
Thank you.
Any other question?
No.
I have a question from TSGCT. Whether G is 1 by R, if so in lossless line, how can both R and G be 0? So G is 1 over R of the capacitance. Remember in the transmission line model we had resistance, inductance, capacitance and conductance G. So this G is representing 1 over resistance of this equivalent resistance of this capacitance. So when I say 1 over R, it is not 1 over this R. It is 1 over R of this capacitance, and we know that ideal capacitor would have its, so let me call it as RC of the capacitance, resistance of the capacitance. For an ideal capacitor, RC is infinite, which means G equal to 0. For ideal inductor, the series resistance of the inductance is 0. So for a lossless line, you have R equal to 0 and G equal to 0. I have CEM connected. Can you ask your question? What is? Can you please repeat your question? Can you type? Because I can't hear you properly. There's a lot of echo. Okay, I have a question here from MLGV. Is there any effect of the frequency of the signal on the impedance matching or on the standing waves formation? Very good question. Influence of frequency. The answer is yes. If you look back, your ZL, the load, it could be a complex load, and ZL could be complex. So you would have, if it is a capacitive reactance, you have XL is omega L. If it is inductive reactance, it is 1 over omega C. So definitely that is frequency dependent. ZL itself is a frequency dependent quantity. In addition, you would realize that your Z naught, go back to the definition of your Z naught. Yesterday we defined Z naught as under root R plus j omega L plus divided by G plus j omega C. Now if R and G cannot be ignored, if R and G are not zeros, then definitely Z naught is also frequency dependent. Right? So in general the answer is yes, the standing wave formation is dependent on the frequency. Okay, let me try and connect to UIET.
Hello. Good morning, ma'am.
UIET, can you ask your question please?
Hello.
Yes.
Good morning, ma'am.
Good morning.
Ma'am, my question is, we did all the analysis we did all the analysis for ideal network. So, what will be the change in the reflection process of the wave in a non-ideal or a practical stage, practical condition?
So even a practical transmission line, you would like to use a practical transmission line with you go back here, here is where we have, right. So even in a practical line, you would try to design the line in such a way that R is much smaller than j omega L, G is much smaller than j omega C, so that the effect of R and G are ignored. A usable line would always have this condition. Now if your question is what would it be if I use a very bad line, right, when I have very large resistance, when I have very small very large conductance, then of course you will have to do this analysis with R and G and the result is no different. You would still get similar reflection coefficient, but then your Z naught would be having R and G and all that. So the answer to your question is practical lines are typically close to ideal lines in terms of lossless nature. Even if it is lossy, you can, to the first approximation, put the value of Z naught with R and G inserted into those equations. The answer would still be the same. Hope that answers your question. You have any other question? I'll go to VP COE.
Good morning, ma'am. Hello, can you hear? Hello.
Yeah.
My question is.
Yes,
my
please.
question is this.
Yeah.
If line is open circuit, that's my observation and doubt. If open circuit, ZL is infinity. No closed path. Then how we?
Right.
If line is open, then ZL is infinity, and there is no closed path. How we can get the reflected wave back? That is the doubt in my mind. Can you elaborate on this?
Okay. So for an open circuit, the question is, how is there a reflection?
What I feel, observation is that if line is open, there is no any closed path.
There is no closed path, absolutely.
Then how we can get the reflected wave? I cannot understand. If you elaborate it.
So
good for
the open circuit is infinite impedance, right? Yeah. Open circuit is infinite impedance, and you would, so the thing is, just its job. You are supposed to be matching the boundary condition. The transmission line is supporting the plus and the minus propagating wave. The boundary condition is allowing a negative voltage to exist in the system. It doesn't mean that it doesn't require a path to be closed for a Z0. Even in short circuit you have a V0 minus. It actually doesn't require a path to close. All what it matters is impedance mismatch. If the impedance is not matched, you have reflection. Think about it in, I mean, I can give you another parallel example. If you think about light that is getting, it's also an electromagnetic wave, it's passing through air, and let us say there is glass, right? There is also a situation of impedance mismatch, and you have reflection happening. We will come to this analogy with an electromagnetic wave a bit later, but a simple answer to your question is you don't need a closed path for reflection.
But we are taking a glass. Something is there. Hello.
Yeah.
Yeah. For this example, you are taking a glass at the end. Glass, some medium we have taken.
I mean, I could take any ZL which is having an impedance very large compared to air. In fact, larger is that impedance of the medium here, more is my reflection. I get in fact maximum reflection when it is open. Now why this is happening in a deeper sense you will understand when we talk about the boundary conditions that the electromagnetic wave has to satisfy. So maybe you will get an answer at that point, because ultimately why this is happening is because when you are talking about voltage and current waves, what actually is propagating is an electric field and a magnetic field, and Maxwell's equations demand that the electric field and the magnetic field have to be continuous at a boundary everywhere. So whenever there is a discontinuity, there is a reflection so that at the boundary there is a continuity established.
Okay.
Right? So that is the the inner reason why do you have these reflections.
Okay. Okay, ma'am. It will be
Okay.
helpful to explain
All
this
right.
thing to my students also. Number of times they are asking such type of questions. Thank you.
This part we will do maybe in a couple of days time when we start talking about electric field and magnetic field and Maxwell's equations and continuity. At that point we will connect it to this point, to the point of reflection. At this moment we will look at it as voltage waves that are getting reflected back and forth. Any other question? I can't hear you.
No, thank you, ma'am.
Yeah. BT, KIT, you have a question?
My question is, what is dispersion free lines? You mentioned
We'll come to
in the
dispersion.
morning.
Yeah.
Dispersion
So
free
I
lines.
mentioned briefly dispersion free is the case when the velocity is independent of omega. When your velocity is independent of omega, which means all frequencies propagate with the same speed. Which means if I excite the system with a pulse which contains say many frequencies, all of them propagate at the same speed. Since we are running out of time, maybe we will pick up this part on dispersion in the next class, and because it deserves a little more attention. Dispersion would create some problems in the line, and we will discuss those issues independently. As I told you earlier, dispersion is something which needs separate discussion. We'll talk about it later. But at this moment, to answer your question, dispersion free line is a line where your velocity is independent of omega. Okay, so if there are more questions, please send an email. We'll take it up at the beginning of tomorrow's class. Wind up today. Thank you.